All right, welcome to the lecture covering 3.3, which is rates of change and behavior of graphs. So we're continuing with the basic fundamentals of functions here. So we're just going to pick up a few more characteristics about functions. Okay, so the first thing that we come to in this section is the idea of talking about a rate of change of some sort of function. And so if you look below the actual gray box there with the notes on it, you'll see a few examples of what the heck is rate of change anyway. So when we talk about how some sort of function is changing between two given endpoints, so if you'll think about our lesson 3.2, we talked a lot about intervals, and if you think about the endpoints of those intervals, if on the graph you can find how much something changes vertically and horizontally between any two given points, then you're talking about a rate of change for that particular portion of the function. So if I make the statement, a population of rats is increasing by 40 rats per week, my rate of change is 40 rats for every 1 week. A car traveling 68 miles per hour. I'm changing my position 68 miles for every 1 hour I'm traveling. A car driving 28 miles per gallon. So for every, 27 miles per gallon. So my gas tank is changing 1 gallon for every 27 miles that I drive. The current through an electrical circuit increased by 0.125 amperes for every volt of increased voltage. So you can see that whenever we're talking about a rate of change, it's some blah, blah, blah changes per every blah, blah, blah. So you're talking about two variables working in conjunction with each other. This is why it translates directly to our graph. So the technical definition is a rate of change describes how an output quantity changes relative to the change of that input quantity. The units on rate of changes are output units per input unit. Average rate of change between two input values is the total change of the function values, so the output values divided by the change of input values. And if you look at this formula here for rate of change, bells and whistles might be going off in your head that it looks a heck of a lot like slope, and that's because it is. So let me just give you a quick visual to help you think about what rate of change is to begin with. So let's say we have this graph. And let's say that this is the graph of a parabola. And we'll say, okay, this is an input value of -1, and let's say that we have an input value of 2 as well. Okay, so if I want to find the rate of change between -1 and +2 on this function, what I'm actually doing is calculating the slope of the line that goes between those 2 points. So I subtract their y values or their f of x values, because remember y is f of x, and then I have my x-axis here too. So what I do is I subtract their y value. So I find the difference, that's the difference in vertical distance. So when I'm subtracting the y values, I'm finding the difference between my vertical position. So I'm finding this right here when I subtract the y values. And I place it over, or divide it by rather, the difference between my x values. So basically I'm finding that right there when I subtract my x values. So it's basically giving me an idea of how this thing has changed from one point on the function to another point on the function. Does that give you a clear picture of what we're actually doing here, Cyprian, when we're calculating a rate of change with something? And I see you're typing, so while you're typing, I'll just explain what these triangles are here. So I have triangle Y and triangle X. Those triangles are actually deltas, a Greek letter. And in mathematics, delta simply stands for change in. So basically, I'm trying to figure out what are the change in my Y values, and I'm going to divide that by the change in my X values to arrive at a rate of change. So Y value per X value change. Okay, so I know, Cyprian, you told me you're back on your old computer, so I'm just going to assume you're okay unless you type something into the chat window. I'll just keep moving forward. But please feel free to stop me if you need to. Okay, so how do we figure this rate of change? Well, we find the difference between our Y values, so that's the change in Y or delta Y, and we divide that by the change in our X position, which is delta X or change in X, and we just find that ratio, and that's your rate of change. So let's take an example here. Gasoline costs have experienced some wild fluctuations over the last several decades. The table below lists the average cost in dollars of a gallon of gasoline for the years 2005 through 2012. The cost of gasoline can be considered as a function of the year. So, we are asked to find the average rate of change between 2005 and 2010. So I'm just going to write, to begin with, the corresponding points for 2005 and 2010. And since we say gasoline price is, or average cost, the cost of gasoline can be considered a function of its year. So that tells me that every point in this plane is set up as Y and C of Y. This stands for year, and that's cost during that particular year. So that's what every point here looks like. So if I want to set up the points for 2005 and 2010, I have the point 2005, and the cost during that year was $2.31. And then I have the year 2010, and the average cost was $2.84. So I've got my 2 points that I need. Now I just need to plug them into my formula for rate of change and simplify the ratio. So I have delta Y over delta X. So this is the difference between my Y values. And you just have to be consistent. So if I'm going to subtract the bottom from the top, I need to do that both in the numerator and the denominator. So I'll call this point 1 and this one point 2. So I'll start by saying 231 minus 284, and that's going to give me the difference between those, and that's divided by 2005. I have to put 2005 first because I put 231 first in the numerator, minus 2010. Okay, and then I go to my handy-dandy calculator because I am terrible at doing decimals in my head. Minus 284, that gives me negative 0.53. And 2005 minus 2010 is negative 5. A negative divided by a negative is positive. So I can just change this to 0.53 over 5. Now, before I reduce this fraction, let me tell you what that means. Since my numerator is my y value, which is my cost, this says every 5 years, because my denominator is my time, every 5 years the cost of gasoline went up because it's positive, up 53% every 5 years. But when you give rates of change, you don't want to state them every 5 years. When you're talking about a rate of change, you want to know what happened every year. So we've got to reduce this fraction. And you do so by just dividing. So when I divide 0.53 by 5, I get 0.106, and now that's over 1. So what this says is gas prices rose an average of, that's 10.5 cents basically, because we know we'd write 10 cents as 0.10. It is 0.106, that's about 10.5 cents. So 10.5 cents per every 1 year. So this is cents, and this is years. So we end up with cents per year. Is that good for you, Cyprian? We understand now what we're doing when we're finding rate of change. You basically have to have 2 points, both having an X and a Y coordinate of some sort. Very good. Okay, so just continuing with this idea, now we're looking at a graph, and we're asked to find the average rate of change on the interval -1 to 2. So the first thing I'm going to do is locate my points that I'm going to be working with. When I plug -1 into the function, I get out 4, so that corresponds to the point -1, 4, and then I also have the point when I plug in 2, I get out 1, so my other point that I'm working with is the point 2, 1. Now I'm ready. I've got my 2 points, delta y over delta x, so subtract my y values over the difference of my x values. And notice, let me actually color code this so it jumps out. -1, 4. I used my 4 first, so I used my -1 first in the denominator. And here I have 2, 1, so both of those values were used second. And it's always subtraction that you're doing between them. So you've got to make sure that whatever point you start with in the numerator, that's the same point that you start with in the denominator. Okay, so 4 minus 1 is 3. -1 minus 2 is -3, which reduces to -1. And I'll just put this, just for understanding purposes, over 1. So this means that for every 1 unit that we went down, and it's down because that 1 in the numerator is negative, and in the numerator we're talking about the y direction. For every 1 unit we went down, we went 1 unit right to get to the next point. So if I draw that line between there, you can see I can travel down 1, right 1, and I hit the line. Down 1, right 1, hit the line. Down 1, right 1, hit the line, and my next point. So we would just reduce this to -1. That's got an average rate of change of -1. Okay, next one. After picking up a friend who lives 10 miles away and leaving on a trip, Anna records her distance from home over time. The values are shown in the table. Find her average speed over the first 6 hours. So, we can start at 0. And so at the 0th hour, when she began her trip, she was 10 miles away from home. And at the 6th hour, she was 292 miles from home. So those are our 2 points. Every point is of the form t for time, and d of t, the function, is the distance traveled. So that's why I said d of t. So I have the points 0, 10, and I have the point 6, 292. Change in y's over change in x's. And let me color code these points again just to be clear. So got my first point in blue and my second point in pink. And I'm going to be dividing and I'm going to be subtracting between the coordinates. Okay? So I start with my y values. That's 10 minus 292 over 0 minus 6. And I could just as easily have done 292 minus 10 over 6 minus 0. It doesn't matter which point you start with as long as you're consistent where you position the coordinates. So if you start with the blue point, you want to start with the blue point in the denominator as well. You start with the pink point in the numerator, start with the pink point in the denominator. Okay. So 10 minus 292 gives me negative 282. And 0 minus 6 is negative 6. Those are both negative, so that comes out positive. Now, before we reduce this, what this says is every 6 hours, she had traveled 282 more miles. So I'm going to divide now 282 divided by 6 to get the hourly change. So that's 47 over 1, and this is miles per hour. So she was traveling 47 miles per hour. That's how you would write that. You good, Cyprian, so far? Okay, great. Oh, what if the line is vertical when the slope is undefined? Oh, that was an old question. I'm sorry, I just saw that. That's a great question. If you have a vertical line, let's talk about that real quick. We'll come back up here. Let's say I have this vertical line, and we'll call this point 1, 3, and we'll call this point 1, 5. So I have 5 minus 3 over 1 minus 1, which is 2 over 0. Okay, so the only thing that you've had happen is vertical change. You've had no horizontal change, so you can't average it. It's considered no change. And actually, you're not going to have this come up because that thing's not a function anyway. And we're talking about the average rate of change of functions. But it's good that you're thinking about this stuff. Now, you can have a horizontal line. Okay, so let's say that this is the point 2, 4, and this is the point 5, 4. Okay, so we would have 4 minus 4 over 5 minus 2, which is 0 over 3, or 0. Your average rate of change is 0 because you're just remaining constant. So think about this. If I get in my car, Cyprian, and I can just automatically be going 60 miles an hour, and I stay 60 miles an hour for my entire trip, the change in how fast I'm going is 0. There is no change. I've got a constant speed the entire time. Now, that's unrealistic because I can't just get in my car and turn it on and automatically be going 60 miles an hour on my way. But theoretically speaking, if I could do that, then, and I kept it right at 60 miles the entire time, there's no change in how fast I'm going because I'm going 60 miles an hour the entire time. What we're figuring out is, okay, well, maybe I sped up to 70 for part of my trip, but then I got into Atlanta traffic and dropped back down to 20 miles an hour, that type of thing. That's what we're calculating when we're calculating the average rate of change. So with a horizontal line, there's no change. So it's constant. It's going to be 0. There's 0 change. For a vertical line, not a function. It's undefined, so we don't even go there. Did that help, Cyprian? I'm glad you asked that. That was an intuitive question to ask. Okay. I'm assuming you're good, Cyprian, so we'll go ahead and move forward. Okay, so these are the types of problems that you're going to see the most of in this section. You're going to be given some sort of function. You don't have a picture of it. You don't have a chart giving you your X and your Y values. You just have a function and an interval. And it says find the average rate of change on this interval. Here are the steps to doing it. What if the rocket is speeding in a vertical line? Then so you're not actually talking about a position of the rocket, but rather your graph is going to have to do with speed at a particular time. So you're not even, if that's your case, you're trying to find your average rate of change of your speed of your rocket, not your position. So let's say the rocket's speeding up vertically, but it keeps a speed of, God, I don't even know how fast rockets go. I'm going to embarrass myself making this number up. We'll say 500 miles per hour. And let's say it's shooting straight up. If I'm remaining constant at 500 miles per hour, my average rate of change is 0 because I'm at 500 miles per hour the entire time. But let's say your rocket speeds up for the first hour at 500 miles per hour and then all of a sudden it loses fuel or whatever and slows down. Now we've created data where we can actually calculate, okay, well, if I started at 500 miles per hour for the first few hours and then I changed to, I don't know, 250 miles per hour, whatever, for a few hours, and then I can calculate my average rate of change. And if it were, let's see, if you really wanted to calculate a rocket going straight up, so let's say and now you get to see my awesome artistic abilities, and I'm being very facetious when I say that. Let's say we have a rocket, although it looks like a fish floating in the sky, and this rocket's going wide open. All right, let's say that at this point, this is at hour 1, and it is, I don't know, 100,000 miles away from the Earth. And then it's still moving up. At hour 7, it is, oh goodness, let's say it's 950,000 miles away from the Earth. So even though it's going straight up, it's not the position necessarily that we're honing in on. What we're graphing is the time in hours as opposed to the distance from Earth. So at 1 hour, it's going to be 100,000 miles, and at 7 hours, it's going to be 950,000 miles. So we're not going to get a vertical line, even though it's traveling straight up in space. Did that help? Cyprian, are you good with that? Yeah, I see you're typing. Okay, cool. Okay, so these are the types of problems we're going to see. No picture, no sets of points, just a function and an interval that you're supposed to calculate this on. So what you have to do is your first step is to find both coordinates of both points. Your second step will be to do delta y over delta x now that you have the points, and then reduce to a denominator of 1. Okay, so I've been asked to find the average rate of change on this function here. F of x is equal to x minus 2 square root x on the interval from 1 to 9. So what I have to do first is find f of 1, and I have to find f of 9. So f of 1, I'm going to plug in 1 wherever I see x in the function. So 1 minus 2 times the square root of 1. And whenever I plug into a function to evaluate, I always use parentheses. It's just a good habit to be in because especially when you start squaring negatives and things like that, it changes if you don't plug it into parentheses. So here I have 1 minus 2 times the square root of 1. Well, the square root of 1 is just 1, so this is 2 times 1. That's 1 minus 2, which is negative 1. So f of 1 equals negative 1. That corresponds to the point 1, negative 1. F of 9, 9 minus 2 times the square root of 9. 9 minus 2, the square root of 9 is 3. So this is 9 minus 6, which is 3. So f of 9 equals 3. That is the point 9, 3. Now I'm ready to actually find my average rate of change. So when you're given just a function in an interval, you have to take that extra step of finding the coordinates of both points before you can say, okay, now delta y over delta x. Okay, so I'm going to subtract my y values, negative 1 minus 3 over 1 minus 9. That's negative 4 over negative 8. Negative divided by a negative is positive, so that's 4 eighths. And that reduces down to 1/2. But that's still not how we want to give an average rate of change. We want a 1 in the denominator, so I need to actually do the division. And 1 divided by 2 is 0.5. So that's really 0.5 over 1. So my average rate of change, we would say, is 1/2. But what that means is that my vertical position changed half a unit for every 1 unit that my horizontal position changed, and it changed in the positive direction. Is that good for you, Cyprian? Okay. Uh-oh. Okay, so Cyprian actually just got kicked out of the room, but I'm going to continue with the lecture because I'm recording for the video. So hopefully he'll be able to get back in. He's been having a few problems with his computer today. All right, as part of exploring how functions change, we can identify intervals over which the function is changing in specific ways. So we can talk about a function increasing on an interval if the input values increase while the output values are increasing. In other words, and this is a very elementary way of looking at this. By the way, you always read increasing, decreasing, and constant from right, I'm sorry, not from right to left, but from left to right, just like you read a book in the United States. So I can think of the increasing parts of the function as going uphill from left to right. And then I also have decreasing. So in an elementary way, we would think of that as going downhill from left to right. And then we have constant. And constant is just leveling off. It's plateauing, just like you would think it would be. We've already studied the constant function a little bit, and that's just a horizontal line. So whenever a function plateaus off and is just flat, has a horizontal portion, that portion of it is constant. You don't see that too often, in the functions that we work with, but it's good to know that it's a possibility. Okay, so I'm just going to point out increasing and decreasing. Like I said, you read it from left to right, so I'll color code this. I'll color code my increasing intervals with this graph right here in this light blue color. So if I start from the leftmost point of the function that I can see, I'm immediately increasing. And I'm increasing all the way from negative infinity up to where I get to an input value of -2. So this is another important thing that you need to know about increasing and decreasing. Increasing and decreasing is it's a y value or an f of x or an output. This is an output phenomenon or thing. Because it's up and down, and that's our vertical direction. However, it is stated as it occurs through the domain. So I kind of have a barrier where I change from increasing to decreasing. So I'm just going to put those barriers there for this particular function that we're looking at. So since I'm stating this through the domain, I come all the way out from negative infinity increasing until I hit -2 in my x value. So my increasing interval, I have one that goes from negative infinity to -2. Notice I wrote a parenthesis with both. It's non-inclusive, and I'll tell you why in a moment. And then I'm also increasing from +2. So I start increasing again here at +2, and I increase all the way through positive infinity. So, and from 2 through positive infinity. Now I'm going to mark my decreasing, and then I'll go back and tell you why I don't include those endpoints. So I'm decreasing here, which starts at -2 and runs through +2. So I'm stating it as it occurs through the domain. So I only have one decreasing interval, and that's from -2 to 2. Okay, the reason that you do not use brackets when you're talking about increasing and decreasing is because at those turning points, which are called points of inflection, at those turning points, at that very value of an input of -2, you are neither increasing nor decreasing. At that point, you simply just are. So you will never use brackets to describe increasing and decreasing intervals. You will always use parentheses because at those turning points where it changes from increasing to decreasing, you just are. You're neither increasing nor decreasing at those points. So those are our increasing and our decreasing intervals for that function there. Now we also have those high and low points, and those are special as well. This point right up here, this is a local maximum. And this here is a local minimum. So if you are asked, what is the maximum? Okay, let me write this down as well. Let me choose a different color. I'll use red. Okay, so if you are asked, what is the maximum? That's talking about the y or the f of x value. So in this case, the maximum of this function, it's at 16. If you are asked, where does the maximum occur? That's the x value that you had to input to get that maximum. And with this particular function, that's at -2. So the what is the y, the where is the x when we're talking about maxima and minima. And maxima is just the plural of maximum. Minima is the plural of minimum. So what is a local maxima? Now you've got a very lengthy definition in the box down at the bottom. But I'm just going to be plain Jane, let's just talk in normal talk. It's a high point. It's the top of the mountain. It's where you change from increasing to decreasing. A local minimum is just the opposite. It's a low point. It's in the valley. And it's where you change from decreasing to increasing. And remember, we read this from left to right. Together, these are called extrema. So when you use the word extrema, you're talking about maxes and mins. That's just kind of the general term for the high and the low points. Neither one of them specifically. Okay, I know you missed a little bit, Cyprian, but hopefully you were able to pick up and catch on when you came back in the room. Are you good so far with this? Okay, awesome. All right, so given this function, P of t, so we have t as our input and p as our output value, identify the intervals on which the function appears to be increasing and decreasing. So the first thing I'm going to do, even if I'm a student in the class, I'm going to color code my increasing and my decreasing intervals. So I hit a decreasing interval first. So I'll do decreasing in pink here. And the way I know I hit decreasing first is because you read it left to right. And the first thing that I hit when I start at the left and move right is going downhill. So this is decreasing. And I'm decreasing, I'm going to put my barrier here. I'm decreasing all the way until I hit a 1 in my x-intercept. And then it looks like I increase to 3, and then I decrease to 4, and then I increase into infinity. So I have another decreasing interval right here. And then I'm going to mark my increasing in blue. So I'm going uphill here and uphill here. Okay, so don't forget, Cyprian, even though this is an up and down thing that's happening, which is a y value vertical type thing, you state it as it occurs through the domain. So I'm going to color code my domain as well, which are my x values. So all the way from negative infinity up to positive 1, I am decreasing. And then at positive 1, I begin increasing, and that goes to positive 3. And then I decrease again from 3 to 4, and then I increase from 4 through positive infinity. So my decreasing intervals are from negative infinity to positive 1 and from 3 to 4. Notice I've only used parentheses because at those points of inflection, at those local extrema, you are neither increasing nor decreasing. You are just a point. So you cannot include those values. And I am increasing from 1 to 3, and then again from 4 through positive infinity. Are you good with that, Cyprian? Because now we're going to take an equation down there or a function down there and go out to our Desmos graph and look at it there so we can identify increasing and decreasing in local extrema. And we'll take a picture and bring it back here on the screen. Okay, so let me write that equation down so that I can remember when I get out to my calculator. X cubed minus 6x squared minus 15x plus 20. Okay. And I'm also going to show you I'm going to tell you how to calculate this on your calculator, on your graphing calculator. Do you have a TI-83 or an 84, Cyprian? Okay, cool. I can tell you how to do this in your graphing calculator and be exact with it. Okay. So let me find where I have my calculator. There we go. Still has our graph from earlier lecture on it, hanging around there. All right, let's delete this. And I want to look at x cubed minus 6x squared minus 15x plus 20. All right, I'm going to have to zoom out quite a bit. And actually, I'm going to hide this so I can have more room to look at my graph. I have to zoom out to get my highs and my lows. This is very skinny. Okay, let me see if I can actually scale this so that it spreads it out a little bit. I want to see on my y-axis from, would probably be good from negative 10 to 10. I want to go from negative 10 to positive 10. Oh, I did my Y. Shoot. Let me reset this. Let's zoom back out. All right. So I need to see from, let's see, I need to see from negative 80, it looked like, up to positive 30. Okay, so my X values need to go from negative 10 to positive 10. There we go. Now it's starting to look a little bit better. And let's see. Yeah, okay. Yeah, that gives us a pretty decent picture there. All right, let me just take a screenshot of this and we'll take it back to our whiteboard. And then I'll tell you how to put this into your calculator. so that you can work with it as well. Okay. And we're almost there, Cyprian. We've got one more slide after this. Okay, so because if I just sit here and notice I'm also asked to find the local extrema with the increasing and decreasing intervals. I could guess at where those high points and low points live. But guessing's not good when it comes to mathematics. We want exact. So if you'll grab your graphing calculator, Cyprian, I'm gonna talk you through how to put this into your calculator so that we can get it exact. And we have a picture of it here on the screen just to go by. So are you ready with your calculator, Cyprian? Okay, very good. At the very top left, you should have a y equals button. Go ahead and click y equals. And before you start typing in our function x cubed minus 6x squared minus 15x plus 20, I want you to tell me, Cyprian, you should have at the very top of that screen plot 1, plot 2, plot 3. Are any of those plots darkened in or highlighted? Because if it is, you're going to have to turn it off first. Okay, good. You're in a good position then. Do you have any other functions already sitting next to y1 equals or y2 equals, or is it just blank? Because I can tell you how to clear them out if there are already functions sitting in there. Since this is an older calculator, somebody may have already used it. Okay, so no functions sitting in there, and we're good to go. All right, so you'll want to just type the function just like you see it. Okay, so to type an x, you have a button that looks like this, and it's in the second row towards the top. It says x, comma, t, comma, theta, comma, n. This is your variable button, and you want to have your cursor right next to y1 equals. Go ahead and type your variable in by hitting that x key, that x, t, theta, n key. And then to cube it, you're going to do the raised to sign, which is all the way over on the right. So let me just say, this is your variable key. And then you have a raised to, so a power key, and it looks like a little rooftop there. And it's all the way over on the right, right above your operations, addition, subtraction, multiplication, division. So let me just stop here and say, did you get the X, and were you able to find the little hat symbol and get that on there, the rooftop? So far on my screen, I've got X, and then I have a rooftop. Are you with me, Cyprian? And I wish I had our calculator on my computer to show you, but the emulator is not compatible with Mac, so I can't show. I guess I could turn my video on real quick. I just will have to turn it off. Cyprian, are you following me, or do you need me to show you my calculator so you can find those two buttons? Too large. I'm not sure what you mean by too large, Cyprian. I'm going to go ahead and just turn my video on real quick and show the calculator so that you can see. Here I am. Okay, so, and by the way, for those of you watching the video, if you're watching the MP4 version of the video instead of the Blackboard Collaborate version, then you're not seeing my chat window right now. Okay, so Cyprian, on your calculator, this is hard to do backwards to make sure I'm going the right way. Okay, so there's your y equals button right there. And it brings up this y equals screen. Okay. Your variable button. Oh, the graph is off the grid. Okay. Okay, well, let me just show the variable button for everybody else watching the video. Your variable button, whoops, I went too far. Having to do this from the back side of the calculator. Okay, my finger's pointing at the variable button right now. X, T, theta, N. And then your raise to button is over here on the right where my finger is pointing to right there. That's how you raise to a power. So here's what you would have to type in to your calculator. I'm going to turn my video off now because my tablet won't work with it. Okay, so you're going to type in x raised to the third power minus 6x again, and then you're going to raise to the second power minus 15x plus 20. That's how you would put that in. And then when you're ready to see the graph, you're going to, let me put it into my graphing calculator so I can walk you through everything. 6x squared minus 15x plus 20. Okay, and I hit graph. Now, you're probably not seeing a very nice picture. Actually, yours says you're saying it's off the grid. So here is a quick way to see the important parts of the graph. Cyprian, right next to your Y equals button at the top is a window button. Go ahead and click the, no, I'm sorry, don't click the window button. Click the zoom button right next to the window button. It's the third button at the top. And what you want to do is you want to arrow all the way down to the 10th entry that says zoom fit. What that's going to do is it's going to zoom however it needs to fit the important parts of your graph on your screen. And then once you arrow down to zoom fit, hit enter. And it should take you back to the graph. And now you should be able to see a sketch of the important parts of it. Oops, I lost the data. It's okay. You can get it back. Just click your Y equals button, and that takes you back to your function. Make sure your function is still there. Once you have verified that your function is still sitting next to the Y1 equals, then click the zoom button and arrow all the way down until you see zoom fit, and that's highlighted, and then hit enter. And it'll zoom and take you straight to your graph. And just let me know, Cyprian, when you got it and you can see that curve on the graph. And then I'm going to tell you how to get an even better picture of what's going on. I'm on the Zoom. Okay, so you're seeing the graph now. Okay, so you can see that even though we're seeing the entire graph on our screens, and let me just show mine again real quick so that those that are watching the Blackboard Collaborate version can see. Okay, so it's a better picture, but it's still not a great picture because you can see how scrunched up it is around the x-axis there. So we can actually draw a zoom box around just the x-axis part so we can see the highs and the lows a little bit better. And to do that, you go back to your zoom. So I'm going to click on zoom again. And this time, I'm going to do zoom box. That's the very first thing you get to. So just hit enter, and it's going to take you back to your graph. And you're going to have a flashing cursor when you do that. And you may need to move it to be able to see it. So you can see I had to move mine around. Let's see. I had to move mine around, and now you can see that. See, it's moving on mine. I'm using my arrows to move that little cursor around. What I want to do with that cursor is use my arrow keys to put my cursor at the top corner of a box that I want to create around the portion of the graph that I want it to zoom in on. So I'm going to leave it right there, and I'm going to hit enter to anchor that corner. Okay, so I hit enter. My corner is anchored. From there, I'm going to move in either the horizontal or vertical direction and watch what happens. So when I start moving horizontally, it's starting to draw a line. I'm going to go all the way over so that I get even that part where it crosses the x-axis again. And then I want to go down, and it's going to draw a box around the part that I want to see it blown up at. I want to see that important part of my graph right there and nothing else. I don't need the rest of the graph. When you get the box around the part of your graph that you want to zoom in on, you hit enter and watch what happens. It zooms right in to that part that you wanted to see. Okay, so I'm going to turn my video off again. Now that we've gotten to that part, we can actually calculate, using our calculator, we can calculate that minimum and that maximum value. So, to do this, follow with me, Cyprian. If you look up at the top, you have a trace button. Don't click the trace button yet because you don't want the trace function. You want the second function on that button that says CALC. That's your calculate menu. So you push the second key. The second key is this button right at the top left of your calculator that's a light blue color. Well, on the TI-83, I don't think it is. I think it's just gray, but it's that key right at the top left that says second. You click the second key, and then you click the trace button. And that's going to take you to your calculate menu. So my trace button's right here. And so you should see your calculate menu come up. Okay, so we have to calculate the maximum and the minimum separately. You can't do them at the same time with these calculators. So the first thing we'll do, since we get to the maximum first, moving left to right on our function there, I'm going to arrow down until it says maximum, until I'm highlighting next to maximum. And then I'm going to hit enter. And it's going to take me to my graph. And you see there's a little blinking cursor on your function. and it's to the right of the maximum that you're wanting to calculate. If you look at the bottom of your screen, it says left bound with a question mark. It wants you to give it a left boundary. So what you want to do is move your cursor along the function using the left arrow all the way. So, sorry. Move it to the left so that you are to the left of that maximum that you're wanting to calculate. And I don't think you can even see where my cursor went. Let's see if I can get a better picture of it for you. There it goes. You see it's moving to the left. And so as soon as I get over that hump and I'm on the left-hand side of it, I hit enter. And you'll see it puts a black triangle at the top of your screen pointing in towards that maximum that you want to calculate. Now at the bottom of the screen it says right boundary. So what you want to do now is give it a right boundary, but don't cross over the y-axis when you do that. So you see where my cursor is blinking. Now I'm just going to arrow right until I get over the top of the hill there, but don't cross over the y-axis. And I'm going to hit enter again. And you'll see it put another little triangle, and they're both pointing inwards towards the point that I want to figure out. And at the bottom of your screen it says, what's your guess? Don't worry about guessing. That's ridiculous. You wouldn't be calculating it if you wanted to guess what it was. Just hit enter, and it's going to calculate that exact maximum for you. So if you look at the bottom of the screen, let me see if I can get this to come in clearly. You can see that maximum, and it tells you it's a maximum. It occurs at an x value of negative 0.999999988, which is basically negative 1, and a y value of 28. So what we just figured out, let me turn my video off so I can write on my screen again. We just figured out that this point right here is the point negative 1, positive 28. So you do the same process to calculate the minimum, but you just choose minimum instead of maximum. So I'm going to write the steps here for you to do either the maximum or the minimum. The first thing that you want to do is second and trace. And that brings up your calculate menu. You want to choose what you want to calculate, either the maximum or the minimum. Once you've done that, it's going to take you to your graph, and it's going to say left bound. That's the left boundary, so you want to arrow to the left of that point you're trying to calculate and hit enter. Then it's going to ask for a right bound. And you're going to arrow to the right. Don't cross over the y-axis when you do this. Don't cross over y-axis or it'll gork out on you. It doesn't understand it when you do that. Arrow to the right until you get to the right of that point you want to calculate on the function and hit enter. It's going to ask you to guess, and you're just going to hit enter. and then it'll give you the coordinates of that point you're trying to calculate. So I'm going to go ahead and calculate the minimum real quick, and you try it too, Cyprian, and let's see if we get the same thing. So I'm going to start by clicking second and trace to go to my calculate menu. And I'm going to arrow down. This time I'm going to the minimum, and I hit enter. I want to cross over the y-axis before I hit enter, so I want to be to the left of my minimum and on my function and hit enter. That's my left boundary. Then I'm going to arrow to the right until I get past the low point and hit enter. You should have two triangles pointing in towards the point you're trying to calculate now. It asks you to guess. Just hit enter. And I come up with approximately, this point right here is approximately 5, -80. Did you get the same thing, Cyprian? Awesome, yes. Okay, so now let's actually, now that we know where these boundaries are occurring, now we can answer all the questions about this problem. So I've got a boundary there at -1 and a boundary here at +5. That's where I'm changing from increasing to decreasing. So the first question says, estimate the local extrema of the function. We did that. I have to repeat it several times to get it. Yeah, the process is tedious, and yes, you'll have plenty of chances to practice in your homework. And you can watch back through this video so that you can remember the steps to doing that. All right, and I'm sure there are YouTube videos just on finding maximum and minimum of a function. So if you want to just find a YouTube video, it'll probably be like 2 minutes long and take you straight to the point. All right, so I have a maximum at -128, and I have a minimum at 5, -80. So if they ask you what is the maximum, that's 28. If you're asked where does it occur, that's -1. If they ask what is the minimum, that's -80. Where does that occur? It occurs at 5. Then it says, use this information to determine increasing and decreasing intervals. So I'm going to come back and mark my intervals. So we'll start with increasing. I'm increasing from -infinity up to -1, and I'm also increasing from 5 through +infinity. I am decreasing between -1 and 5. And we're actually going to end here. I know we've got another page of notes, but this covered everything we needed to cover. I just threw in an extra question just to have more to work on, but we're already way over time, so we'll stop with this one. All right, so our increasing intervals. We have increasing intervals from -infinity up to -1 and from 5 through +infinity. And I have decreasing intervals from -1 to 5. That's what I have for you today, Cyprian. You good to go with that? And I see you're typing. Oh, no problem. Oh, you don't have to thank me for my patience. That's part of being a teacher. If you knew how to do everything, there'd be no need for you to be in my class. I appreciate the fact that you've made a commitment to be here today. So it makes my lectures move better because the students always come up with good questions, and it slows me down too, because if it were just me in here, I'd be flying through this stuff and maybe be going too fast for somebody. So I'll go ahead and thank you for the people that are going to watch this video, that you were here today so that I could go through it bit by bit. Thanks for coming, and have a wonderful weekend, Cyprian.